Hello everyone, welcome to lecture 6.2. We're going to introduce memory coalescing in CUDA. The objective of this lecture is for students to learn that memory coalescing is important for effectively utilizing memory bandwidth in CUDA. We will first introduce memory coalescing and how it originates in DRAM burst. And then we will explain how one can check if a memory access is coalesced in a CUDA kernel. And finally, we will introduce a common technique for improving memory coalescing in CUDA code. This slide shows a system view of DRAM bursting. As we recall, DRAM bursting means that whenever we access a particular location in DRAM, the bytes around it are also delivered through the interface. So this is usually done by dividing the memory address space into burst sections. And here we show a very small example where there are only 16 bytes in the address space, and we divide the address space into 4 burst sections and 4 bytes each. Obviously, this is a very small toy example. And whenever any byte in the first section color that's yellow is accessed, all the other bytes will also be delivered. For example, if we access byte 2, bytes 0, 1, and 3 will also be delivered through the interface. And if we access byte 10, bytes 8, 9, and 11 will also be delivered through the interface. In practice, we will have very large address space. In most of the PCs today, they're usually about around 4 gigabytes or more DRAM in the system. So the physical address space for all these DRAM locations will have at least 4 gigabytes. And the burst section sizes are usually 128 bytes or more. However, the concept is the same. It's just that the sizes are much bigger than our toy example. Now we can define memory coalescing in CUDA. There is no official definition of memory coalescing in CUDA. And because this is a performance characteristic rather than a language characteristic, here is a practical view of how we can define memory coalescing. And essentially, when all the threads of a warp execute the load instruction, and if all the access locations by these threads fall into the same burst section, only one DRAM request will be made, and the access is fully coalesced. Recall that if any byte in that burst section is accessed, all the other bytes will be returned. Therefore, if we only with all the access locations by these threads fall into the same burst section, then only one DRAM transfer will need to happen on that interface. So here we show that if there are 4 threads and each thread accesses a byte in the toy example, and all in that yellow burst section, then we have a coalesced access. And later on, let's say if these threads all access the bytes in the blue section, and we also have a coalesced access. When the access locations by threads in a warp spread across burst section boundaries, we say that the coalescing fails, or the load becomes uncoalesced. And for example, on the left-hand side, threads 0, 1, 2, and 3 access bytes that are 1 byte apart from each other. And in this case, the access locations by this warp spread across 2 burst sections. And even though the access bytes are 0, 2, 4, and 6, bytes 1, 3, 5, 7 will also be accessed and transmitted from the DRAM system to the processor. Therefore, we are wasting half of the DRAM bandwidth by accessing and transmitting bytes that are not utilized. Sometimes we can also still have uncoalesced loads even when the threads are accessing consecutive locations. And this is illustrated on the right-hand side, where the thread 0 access byte 10, thread 1 access byte 11, thread 2 access byte 12, and thread 3 access byte 13. In this case, the reason why the access locations are spread across burst boundaries is because the starting location of the access locations is not at the burst boundary. So if we started with location 8 rather than 10, this access would have been coalesced. In this case, even though the access locations are 10, 11, 12, 13, locations 8, 9, and 14, 15 will also be accessed and transmitted to the processor, still wasting half of the DRAM bandwidth. Now that we know that memory coalescing is important in fully utilizing DRAM bandwidth, and uncoalesced access tend to waste significant portion of the DRAM bandwidth, it's important. Now it should be clear that we need to have a way to judge whether a memory accessing a CUDA kernel will be coalesced or not. Recall that the kernel code will be executed by all threads in a grid, and therefore each memory access is actually a representation of memory accesses done by all the threads. So if the memory access is to an array, and the index into of the array is in the form of an expression with terms independent of thread idx.x plus thread idx.x itself by itself, then these threads will be accessing consecutive locations. And if the first expression end up with values multiple of the burst sizes in the DRAM sections, then we know that we have a fully coalesced access. An important scenario where we need to pay special attention to memory coalescing in a kernel is when we access a two-dimensional C array in a kernel. This slide shows the mapping of a two-dimensional C array into the linear address space. Recall that C uses row major order when linearizing the two-dimensional array into a one-dimensional storage. And we have all the elements in the yellow row that will be mapped into consecutive locations, and followed by the red elements, followed by the blue elements, and followed by the green elements. This slide shows the data access patterns of the basic matrix multiplication kernel that we showed in module 4. And we see that for matrix A, the neighboring threads will be accessing neighboring rows of A. And then for matrix B, the neighboring threads will be access neighboring columns of B. So in this case, when we look at the column access for B, then the column is actually block idx.blockdim.x plus thread idx.x. So this is a form where we have a first expression that is independent of thread idx.x plus idx.x itself. So we know that the matrix B accesses are coalesced. Indeed, when we look at the neighboring threads in a warp, we see that they will be accessing neighboring elements of B, and then they will all go to the next row and access neighboring elements of B, and then they will go to the next row and so on. So this slide further illustrates the coalescing behavior of accesses to B. And during the first iteration, the threads in the warp will be accessing neighboring B elements in the yellow section, and then they will move to the B elements in the red section, and so on. And in every iteration of the memory access, the threads will be accessing neighboring elements in a burst section. So this means that all the accesses to matrix B will be coalesced. This slide shows why the access to the A matrix are not coalesced. Remember that neighboring threads in a warp will be accessing neighboring rows of matrix A. So during the first iteration, thread 0 will be accessed A00, and thread 1 will be accessed A10. And essentially the first elements of rows in the A matrix. So if we look at the top part of the picture, in the first iteration, thread 0 is accessing A00, thread 1 is accessing A10, thread 2 is accessing A20. So these accesses all have 3 elements in between, and the accesses span across 4 DRAM burst sections, and therefore the access is not coalesced. And when we move to the second iteration, the accesses are going to be again spread across multiple burst sizes. And so each of these iterations will cause multiple DRAM burst sections to be accessed, and some of the bytes will be accessed and then transmitted but not used. So in the GPU design, most of the time, because of the massive parallelism, by the time we come to the second iteration, usually the bytes that were accessed from the first iteration would no longer be available to the threads, and therefore we will be triggering new DRAM accesses again and wasting most of the bytes transmitted in that iteration. So this slide shows how the tiled matrix multiplication can remedy the inefficient use of matrix accesses in A. Recall that we're going to be loading tiles of A and B, and then we would be doing a section of computation for calculating each C element after we loaded the tiles. So even though that the access pattern of threads for matrix A will be going down the rows, that is, each thread will be accessing one of the rows in A, but when we actually load the tile, we will not use that pattern. We're going to actually assign every thread to load the A element that has the same relative position as the C element it is computing, and this is illustrated in the picture here, so that when we load, we actually force the threads that are neighboring threads in a warp to load neighboring elements of A. Once the elements are loaded into the local into the shared memory, then they can access the elements from the shared memory in their original row traversal. So and the most important point is that when the data is loaded from DRAM, the neighboring threads should be accessing neighboring locations, and this is done in the loading process for the tiles. So if we look at the access timing, we see that we have two distinct parts of accesses. One is accessing from DRAM into the shared memory, and this is done by having the neighboring threads to access neighboring locations. Once we have loaded the elements into the shared memory, then the neighboring threads can now just go through neighboring rows of A in the shared memory. And so we see that in those two phases, the neighboring threads will be accessing horizontally neighboring elements in the orange horizontal line, as we showed on the right hand side of the small blue tiles. Whereas once we have finished the loading, the accesses to A is then performed in the vertical pattern. So we see that the threads actually have 90 degrees of turn in terms of the access direction, whether it's loading from DRAM or it's actually accessing from the shared memory. And this is what we call a corner turning technique that essentially forces the threads to access DRAM in a more favorable pattern. And then once the data gets into shared memory, because shared memory is designed with the on-chip memory technology, which is not DRAM technology, and then that's where the access directions no longer matter. And then so we say that we turn the corner, and now we can use the data the way that the original algorithms dictate. GPU programming. This is the end of the introduction to the toolkit. Thank you.